Hey everybody, thanks for joining us today. We can kind of dive in. So just a quick overview of what we're going to talk about today. So we're going to talk about SLS 3D printing, but we're also going to interview Mike Dorna with Briggs Stratton about his experience with his SLS printer. And then we're also going to do a pretty deep dive with Brian Carr from 3D Systems on some of the software features and kind of some of the different things that you can accomplish with SLS. So just a quick introduction of our company, Nota3D. If you haven't already had any experience with us, we're a 3D Systems partner. We're based in the Midwest, though we do span across the entire US. We represent the full line of 3D Systems equipment, including the NextDent 5100 and the full portfolio of Geomagic software. We specifically focus on 3D printing. Our entire company is dedicated and devoted to 3D printing. So it's not just a line item for us. We're very passionate about this industry. We take a very specific approach on how we work with our customers. You know, I think of it as you wouldn't feel very good if you went to a doctor and he just wrote you a prescription or suggested a surgery before he even, listened to what was wrong or what your problems were. And so, since we offer a very wide range of 3D printing solutions, there's no 3D printer that's just good at everything. So we have to take a lot of time to listen and understand your process, understand your problems, and understand what your goals are. So what our process is, we usually like to listen to what you have to say, then that'll help us narrow down some solutions. And then from there, we can experiment, we can evaluate some of those solutions and hopefully come up with, whatever the best solution is to resolve your issues and help achieve your goals. I'm hoping to be able to have the opportunity to meet and listen to some of you that are on this call today. So I'm excited to talk to you guys about 3D Systems, SLS 3D printers, and how investing in this technology could help your business. SLS, which stands for Selective Laser Sintering, is unlike any other 3D printing technology because it prints parts that are every bit as strong as injection molded plastic parts. No other print technology delivers what SLS does: production grade parts that meet or exceed engineering requirements for strength, durability, heat, chemical resistance, and biocompatibility. SLS is a robust process that makes robust parts. And how we're doing that is we're fusing parts together with heat and directed laser energy. SLS printers are big and they look like industrial production equipment because they are industrial production equipment. So 3D Systems is kind of making a splash in production with, SLS is a big way that we're doing that. These are just a few industries that are using SLS extensively. So, one of the main adopters of all 3D printing technology is automotive. We're helping them with compressed product development cycles, functional prototypes that meet heat, strength, accuracy, and mechanical requirements, bridge production, toolless manufacturing of injection mold quality parts. With aerospace, we're helping them increase, faster time to market, lightweight, high value production plastics, improved assembly through custom jigs and fixtures. Healthcare, improved surgical outcomes through patient specific surgical guides. We're doing production of personalized devices for prosthetics, orthodontics, hearing aids, and more. Industrial parts, we're helping streamline supply chains. We're giving the ability to have more flexible production, rapid customer responsiveness, tooling, 3D printing tooling, including molds, fixtures, jigs. It's faster than traditional tooling. And footwear is actually a big part as well. So mass customized products that, ideally will fit every customer perfectly. As I mentioned, SLS makes production possible. These parts are just about as strong as molded parts and superior to all other plastic 3D printing technologies. The only 3D printed parts that are going to be stronger than our SLS parts are from our direct metal printing systems. You can find SLS parts in UAVs, they're on F-18s, Bell helicopters, and fuel tanks and transmissions. So right now, if you need production grade nylon parts with tough mechanical properties, SLS is going to be your best option. So I've already noted that SLS produces parts that have comparable properties to injection molding, just slightly lower on the impact and elongation. Now let's compare what happens when you run nylon 12 through SLS versus when you run it through FDM. It's very clear that the process matters. The SLS print process yields parts that are superior in almost every single way, even when they're both made with essentially the same material. And the FDM process just results in micro voids between each layers, which makes the parts a little bit weaker. But there's a huge benefit when it comes to speed. So there's simply no faster way to get these strong parts. A real world example that we took here would be, let's say you needed 250 parts that are about 2 inches by 2 inches. The Pro X SLS 6100 takes about 33 hours from the time you load the CAD file into the software until you have finished parts in hand. FDM would take almost 10 straight days of printing plus hours of manual support removal to make those same 250 parts. And then of course, to go to soft tooling and mold a run of those parts would easily take 2 weeks to get the tools, plus a few hours for setup and then shoot the parts. So having an SLS printer in-house could dramatically speed up your production cycle. One thing that people absolutely love about SLS is that it doesn't require any support structures. The powder surrounding each part holds it up while each layer is printed. So when the parts are done, all you have to do is pull the parts out of the surrounding powder, use pressurized air or brush to clean off the residual powder, and that's it. There's no supports to pry off, no additional steps to cure or bake or anything else. This also means that you can print more types of geometry because you don't have to worry about how to support certain shapes. So this is a quick snapshot of our current SLS portfolio, ranging from 60 liter to 230 liter build volumes. The Pro X SLS is the newest and the next generation of the SLS platform. So the Pro X SLS 6100 is the newest of all of our SLS systems and is the most automated of all the SLS printers. It has a integrated material quality control system, which we call an MQC. And the 6100 is the best choice when you need high surface quality and mechanical properties. The S Pro series are a little bit more flexible in terms of materials, especially the S Pro 60, but they don't feature the level of automation that the 6100 offers, and it doesn't offer the entry-level price point. But they do enable additional materials, and we do have 2 larger build volume options with the S Pro machines. But for the purpose of this webinar, we're going to focus on the Pro X SLS 6100 as it is the newest SLS platform. This machine is excellent across the board from production to prototyping. It offers a very attractive total cost of operation and ownership. Many people have an outdated image of SLS, and that's kind of what sparked the whole reason why we wanted to do this webinar, is because we talked to a lot of people that, have maybe used SLS back in, the 90s or early 2000s, or they just have an image that SLS is very messy. There's powder everywhere. It's very manual, and that's changed a lot. And so that's really what we wanted to focus on here. And the 6100 offers automatic material handling, which makes the process significantly cleaner and also saves time and money. Using the Duraform Pro X nylon materials, the 6100 delivers best-in-class part quality for demanding end-use and functional prototyping applications, as well as a 20% total cost, lower total cost of operations when you compare it to similar printers. The material quality control system, so the MQC, provides automatic blending and recycling while providing transportation of the material to the printer, so you don't ever have to get hands-on with the powder. Auto nesting is also a key feature of the 3D Sprint software. It's going to help optimize part orientation in the build area, and we're going to kind of dive into this a little bit further. But maximizing the print capacity without sacrificing quality. You're going to get a lot more parts per build, saving time and minimizing waste. So I briefly talked about the MQC, the Material Quality Control System. So there's two different MQCs available right now. There's a single MQC, which supports one printer, and then there's the dual MQC, which supports two printers. The MQCs come with a user interface screen that lets you define the material blend ratio in 5% increases on the single, and then up to 1% steps on the dual MQC. There's an integrated remote cooling station, material tracking, a downdraft table to recycle the unused powder, and then, as we talked about, automated powder blending. So now we'll kind of dive into some of the different materials that are available on this machine. 3D Systems has Nylon 11 and Nylon 12 in both black and white. We also have aluminum filled nylon, glass filled nylon, high temperature, plus we have USP Class 6 and food grade certifications. The Duraform Pro X EX is our standard Nylon 11. This is great for durability for long life, excellent impact resistance, fatigue resistant for applications like living hinges that require hundreds of open and close cycles. So this is a really, really great application for this material. Fuel and oil resistance, which makes it great for automotive applications, and the parts have the toughness required to replace injection molded ABS and polypropylene. Duraform PA, now this is our standard Nylon 12 powder. Strong, tough thermoplastic, stands up to the rigors of long-term real world testing, and we can also use this to replace traditionally injection molded parts. Excellent mechanical properties, outstanding surface smoothness, stable dimensional and mechanical properties over time, and this material is biocompatible and food safe. There's not really a whole lot of technologies or materials out there that can claim the food safe. So the Duraform Pro X GF, so that stands for glass filled. This is excellent materials, mechanical stiffness and elevated temperature resistance. This is dimensionally stable. It's easy to process. It has a very, very nice surface finish, and it's accurate and repeatable. So it's a great, great material to be able to use for those types of applications. Now, one that's very unique to our SLS machines is the aluminum filled nylon. So this gives you a nice aesthetic metallic finish directly off the printer. Complex designs can have that metallic look with the functional strength at an affordable cost. Repeatable mechanical properties for consistent parts. It's easily machined and polished for additional press fits, tapping, or other uses, and it offers excellent stiffness to weight ratio. And then the last material we're going to kind of dive into here is the Duraform Pro X HST. So this is a fiber reinforced nylon 12. Again, this really helps with elevated temperature resistance. It's a high stiffness and strength to weight, and it's just has a really, really nice surface finish. So it's non-conductive and it's RF transparent as well. So we kind of touched on our 3D Sprint software a little bit, and if you've watched any of our other webinars, we talk about 3D Sprint as well. So 3D Sprint actually drives every single one of our 3D printers outside of the metals technology. So you can, we have lots of customers that have different 3D systems, equipment in-house, and it's really nice to just be able to use one software to drive all of those printers. So for SLS, there's no need for, a third-party software. The tools for high performance, high density 3D nesting. There's quality checks for pre-build verification. And there's also the ability to build a sinter cage. So there's kind of a structure generator in the software that Brian's going to dive into later in the webinar when we do the software demo there. So Auto nesting is a key feature of 3D Sprint, and it will optimize part orientation in the build volume area, maximizing the print capacity without sacrificing quality. So if you can get more parts on the build, then you're going to save time and you're going to save money, minimizing waste. The software allows parts to be added even after the build has started. So that's kind of a unique thing as well, because most of the time, once you press print on a machine and you go, and then an hour later, one of your colleagues comes over and says, "Oh, you already started the printer. I had some, parts I'd love to throw on there." They're kind of stuck. So with SLS, this actually gives the ability, a little bit more flexibility there. So which is pretty cool. So this is fairly new. It's 3D Connect is 3D Systems Internet of Things platform for additive manufacturing, which hosts a suite of software solutions to increase, printer uptime, production efficiency, and improve customer satisfaction. So the two main things that 3D Connect helps us offer is better service. We're having a direct link to the service department is beneficial for the end user. And then just more uptime, being able to preemptively see an issue before it actually becomes a problem is the goal. And that gives our customers more uptime and faster service. So that's kind of our quick overview of the 6100 here. Didn't want to take too much time and get in too deep with everything. So this was a nice overview. We're gonna have Mike from Briggs Stratton kind of talk next about his experience with SLS, and then we'll also dive into the 3D Sprint demo. But the key for this webinar is really to give you guys kind of a basic understanding, hopefully update your image of SLS, and then we'd love to dive into that further with you guys, get you guys some sample parts built, or just hop on a call to learn a little bit more about what you guys are trying to accomplish to see if SLS is going to be the right call. So up next, we're going to pass it off to Mike at Briggs Stratton. I think I just have to stop sharing my screen here and we'll go from there.
I'd like to introduce Mike Dorna, who is the manager of Briggs Stratton's Research and Development Rapid Prototyping Center. Mike has been instrumental in the product development and rapid prototyping activity at Briggs Stratton for over 30 years. I was involved with the evaluation, justification, purchase, and implementation of 3D Systems Selective Laser Sintering System. He also was in charge of several other Stratasys large frame Fortis and Polyjet 3D printers. Mike, thanks for joining us today and sharing the challenges of your responsibilities at Briggs Stratton and your experiences with the SLS system. I'm sure many of you joining us today have similar obstacles in your companies. Mike, could you tell us a little bit about what you and your staff does at Briggs Stratton and how 3D printing is benefiting that activity?
Sure, absolutely. First of all, thank you, Tom, for hosting me and having me showcase some of the great work we're doing here at Briggs Stratton, improving existing technology and also bringing new technology to the market. Exciting times here. As Tom mentioned, I manage the Rapid Prototyping Center in Research and Development. We're right next door to corporate headquarters in Wauwatosa, Wisconsin, which is a suburb of Milwaukee. I manage a 9-person shop. We do all the prototyping and concept work for research and development and product development, and also concept development. So we're taxed pretty hard, really busy almost always. Fun times. So the shop, we have a heavy emphasis on CNCs and technology so that we can do our jobs as quickly as possible. My team focuses on the subtractive side of prototyping, the machining side, and I manage the workflow through the shop and also through the 3D printers, which I operate, all our 3D printers. We added our first additive capabilities about 7 years ago now with a couple of FDM machines. And we also had an Eden Polyjet, Eden 260V Polyjet. That got us started in the additive side of rapid prototyping. When I got into it, I knew absolutely nothing about it, and I learned really fast. we made a few changes since then, and also probably the biggest change we made was adding the 3D Systems Pro X500. That was a huge benefit for us. We used to spend a lot of money on the outside getting rapid prototype parts done, mostly SLS parts, and we save, that investment paid off very quickly. Those machines paid for themselves. We're realizing a 35 to 60% cost savings on every part we print.
Wow. It sounds like there's a lot of advancement in your shop. Didn't you recently bring in a Waterjet also?
I did, we did. That was actually recently, yeah, that was actually 3 years ago next week.
Okay.
And that had a huge impact on how fast we can get things done. That's another piece of technology that really impacted us. There were a lot of people that didn't really see how it would, including myself, to be honest with you. It just made a huge impact. Thanks for bringing that up, by the way.
Yeah. It sounds like providing fast, robust components to shorten the development and testing cycle is a pretty big part of the service your model shop provides to the various departments and engineers at Briggs Stratton. How did the demanding requirements of those models influence your decision to bring in the SLS system or any technologies when you already have a couple other large frame FDM machines?
Well, like I mentioned earlier, we started out with the FDMs, and I wasn't even aware they existed when we got them. It's a long, convoluted story, but I ended up with them. They were actually investigated by another department, and then the decision was made to bring them into R&D. So that's where I came in. So interestingly enough, no one else in the corporation really knew about FDM either. So word spread that I had additive capabilities up here, and people started sending me files to print. And their first question was, "What's FDM?" And I said, "Well, I explained it to them, and then I said, just let me make you some parts, and if you don't like them, we'll discuss it." But it quickly took off from there. Response was very positive. I knew that SLS was in our future, though, because we had a new VP in research and development, and he came from a product development background, and he had an intimate understanding of the benefits of SLS. I really didn't want an SLS machine in my shop. My shop's really small. We don't have a lot of room. I had done some investigating knowing he was interested in SLS, and I was looking at what was known as legacy machines or they're now known as legacy machines. A lot of manual operation, meaning you mix the powder yourself. You have to preload the machine with powder. It just, every place I went that had them, it looked like a mess. And I was going to be the one running these, and I kept balking at it. We were working with a vendor at the time who mentioned that 3D Systems had a new technology in the Pro X500 that was pretty much self-contained. It mixed, it had a device on it, a complementary machine to it that's known as a material quality control system, I think it is, an MQC.
Yeah.
Short. It piqued our interest, and the more we talked about it, and we had visited with 3D Systems a number of times, and we decided to pull the trigger. And I flew down to Rock Hill for one day just to check this thing out. I had no idea what it looked like, how big it was, any of that. I mean, other than the dimensions, but I wanted to actually physically see it. So I went down there and we checked it out, and yep, we got it. And completely automated. We have probably literally millions of dollars worth of CNC machines right outside my office that are in close proximity to the Pro X500 and the MQC. And the dust that you would expect to find on everything just isn't there. There's an air handling system that does a really good job of filtering the area when you do a breakout, when you take the part cake out of the machine and break it out. Just expand a little on the MQC. You bring the part cake over to the MQC and start. It's like an archaeological dig. You start digging through the powder to find your parts, and you turn on the air handling system, and there's vents on the MQC that draw the dust into the air handling system and into a filter. There's also a sieve, so residual powder that isn't a part gets pushed into there, and that automatically sifts it and mixes it with fresh powder that's preloaded into the MQC, and that creates your blended powder that then also automatically gets fed to the machine on demand. It's a great system. Works fantastic.
Yeah, it's interesting because there's been so many advances in the technology over the last 20 years. A lot of people have the misconceptions that it's the old process, and they're not aware of the new material handling systems that are involved. Anyway, so having a complete model shop with CNC and the numerous 3D printing technologies of SLS and FDM and PolyJet gives you a lot of capability. How do you determine which particular system to use on a project?
We have a Google order form sheet that somebody in IT set up for us. So people go to our internal website and they can pick either a machine part or a 3D printed part. That'll take them to an order form, and in that form they specify obviously their name, email address, etc., project number, charge number, things of that nature. But it also allows them to pick the technology and the material. Obviously with the SLS, it's only one material. The FDMs, they have a couple of choices. So that works really well for the most part, except some people don't realize the limitations of any one technology, or perhaps their part size is very large.
Right.
And they really need to, I then have a conversation with them, either a quick email or a quick phone call, and discuss, your part is bigger than the SLS part build, so we're going to do it in the FDM. Is that okay? And that kind of thing. By now, most of my customers I've dealt with for like the last 7 years, they know what they want. So
okay.
I usually, sometimes it comes down to time. Like if the SLS is backed up, it'll go in the FDM just to help somebody get their part. Most of our parts are for fitment and styling, things of that nature. We do obviously use the SLS more so for actual part testing, because it's a closer to what the final product will be as far as fit, finish, and function.
Okay. Well, the SLS system has quite a wide range of material options. What materials are you currently using, Mike? And what do you find to be the most useful of the materials for your applications?
For the SLS?
Yes.
SLS, we only run Duraform PA.
Okay.
That's the only, we don't change.
Which is a nylon.
Yes, sir.
Okay.
Nylon. And that can lead into this interesting story. When we first got the SLS, one of the engineers or engineering managers called me, and he wanted to know why we didn't he had heard what we decided to go with for materials. And he wanted to know why we didn't go with glass filled and nylon. And I said the Duraform PA nylon, it will serve a broader range of applications. It can make small detailed parts. It's got flexibility to it, and so I explained all that. And he didn't like that answer because he always ordered glass filled parts from outside vendors. And I said, well, what are you trying to accomplish here? What part do you want to build that you don't think this is going to work? So we built an intake manifold for a V-twin, and so our V-twins look very similar to a Harley Davidson, to be honest with you. So there's an intake manifold that spans the two cylinders that are roughly on, I think, 45 or 60 degree angles. I should know that, but I don't. So I printed this part, this intake manifold. I cleaned it up. I made 6 of them actually, and then we seal them with basically a hobby shop epoxy, 30-minute epoxy. Mix that up. Mix that 100% with IPA, isopropyl alcohol, and you get a very, very viscous, very fluid coating or mixture. And I just take a basic throwaway acid brush and brush that as much as I can on the inside of the manifold and also all over the outside of the manifold. And that seals it and gives it a little more durability. And called the guy up, said, your parts are done, and they started running them. And I didn't hear anything. And a couple of days later, I received orders for 6 more, and then I received an order for 12 more.
Wow.
I started, yeah, wow. So I started talking to some people, and I said, well, what's going on? Are they breaking? Are they not holding up? Why do we keep ordering them? You know, we could go on the outside and get glass filled if necessary. I said, no, they're actually working great, and they're putting more engines on test with these parts.
Wow.
I said, okay. So I said, so what's the end game here? You know, what are they trying to accomplish? And they wanted to verify the design. And to do that, they ran at 2,000 hours at wide open throttle, which is an absolutely brutal environment. If you can imagine, it's an air-cooled internal combustion engine, and they held up. So that's our big success story with the SLS. We had other ones, but that one was the one where nobody questioned it anymore, whether the material was correct or.
That's pretty amazing. Prior to using a additive process, how did you create those manifolds, Mike? Was it machined out or cast?
Yeah, those would have been done. Oh boy, you're bringing back nightmares for me. Those would have been done as I remember way back, they were cast iron castings. That's how.
Wow.
Then we did aluminum castings, but they were very rough sand castings. Right?
Okay.
And then they had to be machined. A lot of times we had to figure out a way to clean out the inside of them, and that was very interesting, very time consuming. But yeah, that's how, and that's quite a process because you're committed to the part then, right? I mean, here we can change designs. Why? So that's how we would have done it. Yeah.
Wow. Wow. Well, times are changing with this COVID issue. It's affecting many businesses. We hear this every day. So I assume maybe your activity is a little slower in the shop than it was back before the COVID hit. But back then, or even now, how busy is your SLS system in comparison with even the other printing technologies you have in house?
Actually, the COVID, because designers and engineers can work from home relatively easily. And they're still producing parts and drawings and part files for us, and we have remained quite busy, especially on the additive side. Right now, my FDMs are backed up almost 3 weeks.
Wow.
And the SLS runs at least once a week with a full build, or a couple times a week with a partial build during all this. It depends on what stage of the project we're in. If it's the beginning, and they want a lot of different parts, and then parts will change over time for a myriad of reasons. But about a year ago, maybe not even that long, I would run that SLS machine 4 times a week, back to back. So I'd set up builds, and they were backed up. I'd have 3 full builds. So the build area is roughly 14 by 16 by 18. Okay, so as many parts as I could fit in there. And most of our parts are relatively small, compared to like an automobile industry or anything like that. So we were able to, I'd start a job, okay, let's say Monday morning. That build would run for 40 hours. So Tuesday afternoon, it would be done. Tuesday afternoon, it'd be done. I would pull that out hot, right? Which you can do, it's not a big deal. Put it over on the MQC, and there's it's really not a cooling system, but it's to keep the powder as pure as possible. There's a lid that goes over the carrier of the build, and that pumps just a little bit of nitrogen. Yes.
Yep.
Into the build, just to keep it. It's not really cooling it. It cools naturally. It just keeps, like I said, the powder pure. So I do that, clean up the machine, do the PM on it, and start another job. That whole process from what I just described, pulling the build out of the machine to starting a new, build, I can do that in about 30 minutes. So do that, start another build. That build's done, and then I'd start another build Friday that would run over the weekend and start the whole process again on Monday, okay? So we did that, and this is, it's gonna sound like an exaggeration, but it isn't. Over for at least 3 months straight, about a year ago.
Wow.
And that machine just, it never misses a beat. I rarely have any issues with it. And if I do, they're immediately addressed.
That's great. That's great. Hey, I had another question, Mike. It sounds like these parts are pretty durable for what you're using them for. Have you ever had a need to use these for a production part where you didn't want to tool up for it, or you had a very low production volume, maybe a dozen or something?
Not off the top of my head. No, I've made tooling fixtures. I've made fixtures that hang on to maybe like the side of a tractor so they can place the emblem on there. I've done things like that. I've done production supplemental, I'd call it.
Yeah, yeah. Well, to sum it up then, what would you say are the main benefits that Briggs Stratton has realized as a result of having your SLS system?
The ability, the biggest one is to control the cost, right? It's a whole lot cheaper to do it here than it is anywhere else. The speed of it, right? I can outside sources can turn them around pretty fast, but sometimes they can't. I can, if depending on what the priority is and who it's for, I can get a part overnight. And also depending on the size of the part, of course, and the quality. We can control the quality. So cost, speed, and quality for our
That's the name of the game. Well, Mike, hey, thanks again for sharing all your experiences with us today. If anybody out there watching the webinar today have any questions for Mike, send them in. We'll get them over and we'll get you the answers. So again, thanks again.
Thanks for having me. It was a lot of fun.
Appreciate it.
Again, Tom.
Yeah.
Awesome. Well, yeah, Mike is a great guy. I've known Mike for I don't know, probably coming up on 7-8 years now, and so he's awesome to talk to. So if anyone on this webinar has any interest in talking with Mike, directly about specific questions or experiences, definitely let us know, and I'm sure he would be open to having that conversation. So now the next portion of this is going to be a deep dive into 3D Sprint with Brian Carr. We did actually pre-record this with Brian due to scheduling conflicts. So I'm just being upfront that this portion is about 30 minutes long, but it is really, really good information. Brian is very passionate about SLS. He basically has been involved with DTM, who invented SLS back in the late 80s, early 90s, and he's been with the process, all the way, 30 plus years now. So I'm going to pass it off to kickstart that. But if you don't want to hang around, we will be, we are recording this whole thing, and we will be able to send that out to you as well. If you have questions or you want to request sample parts or get more information on these machines, please feel free to reach out to us. It's just info@nota3d.com. You can also send us an email or go to our website, which is just www.nota3d.com. So we also are going to be having a SLA webinar coming up. So keep an eye out for that as well if you want to learn more about that. So, but all right, going here, we will kick off the 3D Sprint demo with Brian.
My name is Brian Carr. I'm a member of the Applications Innovation Group at 3D Systems. 3D Systems is the world leader in 3D printing technologies. And one of those technologies that's near and dear to our heart is selective laser sintering. Selective laser sintering takes powders, typically nylon powders, and fuses them under the energy of an infrared laser. It preheats those powders under the energy of infrared lamps, and does the layer-wise process over and over again until you have a solid three-dimensional thermoplastic part in your hand. To prepare an SLS machine for operation, you need some build prep software. Historically, 3D Systems has used a software called Build Setup. Build Setup was written on architecture, computer architecture that has now been superseded. So generally, even though computers are faster now, it's still relatively slow. It's a bit cumbersome, and it doesn't do some things that new improved software does do. The new improved software for 3D printer build preparation is the 3D Sprint software. And 3D Sprint works on several of the printers, but today's focus will be on SLS. SLS has some charming advantages over other 3D printer technologies. Most specifically is the lack of support structures. We'll talk about that when we introduce some STL files into this virtual build volume that you see on the screen. So you open up the 3D Sprint software. The version I have right here is running in a standalone mode. I'm in a home office miles away from any SLS machine. So what the build preparation software does in a very automated way is it lets you drag and drop STL files, step files, IGES files, solid part files, lets you drag and drop them into the virtual build space. And then at your discretion, we've made it pretty easy to do, at your discretion, set the job up for the attributes you care most about. I'd like to demonstrate that now. So if I come up here and I say, let's import some files. So I will select all of these. And then I'm going to deselect the ones I don't want to bring in. So now I have everything ready to go in. And we see now that everything is annotated with a green check, telling us that the software has given them an inspection for the goodness of the CAD. And it's also given us a verification that we are within the allowable build volume. I can see now that we also have a slight problem here. We have parts where the units are wrong. I'm going to change the view to the top, and then we'll zoom in on these parts. We'll select them all, scale by unit. Voila. Okay, we made them the big parts that they're supposed to be, but we also moved them out of the allowable build volume. We can auto place these now, and voila. Oh, that's a full-size version of this part. For those of you who are unfamiliar with some of the sample parts that 3D Systems shows, that big manifold in yellow is an intake manifold from a Formula SAE car that was built by the University of North Carolina at Charlotte. We rendered this part in our Rock Hill CIC out of GF material, and they ran it on their Formula SAE car, and it worked. Pretty cool. It's too big for this demonstration. I'm going to go ahead and just delete it, and we'll move on with everything that fits nicely into the space. So I started this discussion by suggesting that SLS doesn't need support structures, and that's one of the many charming things about it. As an operator of SLS, the first decision you make when you want to build a part is deciding, are there attributes of that part that I want to build in the most optimized way? If layer lines, like any layer-wise process, SLS, SLA, DMP, MJP, any of the layer-wise processes are going to have layer lines, and you get to decide how you want those layer lines to impact the part. The reason you get that decision is in technologies that have support structures, you may choose an orientation that minimizes the impact of supports, the appearance of supports, or the effectiveness of supports. In SLS, since we don't have supports, we can in fact make decisions based on other outcomes. all of these round parts that you see, this swirler, these exhaust collectors, this small version of that propeller, all of them have generally round features. And as a guideline for SLS, I would say let the scanner, the digitally encoded high torque motors that drive the mirrors that steer the laser beam around the space, I say let the scanner draw those features. So what you see here is a good orientation for feature reproduction, letting the slices be generally round, and you get a good outcome. It also means, and we'll go to an ISO view so that we get a sense for the impact on the height of the build. We also see that it's not as short a build as could be. Coming over here to this properties panel, we see the Z extent says 124 millimeters, so it's 5 inches of build required to get this job out as we see it here. If we're so inclined to say the parts are going to not have a high level of scrutiny put on them, let's decide to build them as fast as we can rather than as pretty as we can or as well as we can. We can tell the software in an automated way. I just hit Control-A to select all. We can tell the software in an automated way to orient all of these parts so they build the fastest, okay? And if we make the decision here in the Orient screen, running an auto version of Orient, if we make the decision to let print time be our guiding principle, then it's going to lay all of these things over into the flattest that they can. And as you can see, it also created a bunch of collisions. At that point, we would auto place, and we would start to use the auto place tools that let it become, I won't call it artificial intelligence, but you'll let it start to think about stuff to give you the best nesting of the parts in there. So what I'm going to do is I'm going to tell it I want height to be the priority. I'm going to allow it to rotate the parts around Z if that lets it nest more efficiently, and then we'll send it on its way. So it might not look like much, but we just saved 70 layers. Wait a second, no, I'm not looking at the right one. We just saved 250 layers, roughly 250, 300 layers. We went from 125 millimeters down to 95 millimeters. If you look at this portion of the screen, it's telling you what kind of printer in what kind of mode we're setting things up for. It's telling us that we're setting up a 6100, running the Duraform Pro XPA, nylon 12 material, and the mode is standard production. Standard production has 0.1 millimeter layers, which is 4,007 inch. So in a very automated way, letting the decisions be made by the software, I was able to get this job ready to go, and it happened pretty quick. Now, I mentioned that the parameters are assigned. These parameters that are assigned are default parameters. It turns out that you may, over the passage of time, decide to use some unique parameters for a particular part type or a particular job. And if that's the case, then you come up to the parameter editors. I just opened up the scale and offset editor. Scale is the value that we grow the part by to accommodate shrinkage. And you can see it's roughly 3% in the X and Y, and a little better than 2.5%, 2.4% in Z. So we grow the parts by these scale factors to accommodate shrinkage. That's going to happen when they return to room temperature. When we do our slicing in SLS, it's a pretty simple raster fill pattern, and we offset the raster lines that we draw. We offset them at their beginning end and their finish end to accommodate for laser beam diameter. So in the scale and offset editor, we've created using the default values as I've done here. These are things that are going to happen to each of these STL files, sort of behind the curtain. You won't even notice it's going on. Using the default parameters, let me select any one of these parts. using the default parameters for the bill, I'm sorry, for the part, you see that there's a fairly small set of visible parameters in the normal mode. You tell it how hot to hit it with the laser on the fill vector. You tell it how much power to use on the outline, which is a border, if you're familiar with the SLA terminology. You can tell it to do the fill vectors, the parallel vectors first, or you can have it do the border first. But there's also other parameters that you can turn the knobs on if you choose to. So I'll show you those by clicking the All button, and you see there's a variety of things that you can do should you need to tailor the parameter set for a desired outcome. It's our firm belief that these parameters after installation of the machine are rarely touched. The field engineer comes out with a power meter, he sets the power, he does a build, and people running our gold standard material Durform PA find that they just don't have to change parameters on these more stable modern machines. Finally, there's a third parameter editor, a parameter editor called the build profile editor. And this is the things that affect everything in a build. Temperature, for instance. We can't affect temperature for one part. But we can for one layer. So the things that happen to the whole build are adjusted here. So we typically find early on in your relationship with SLS, you'll seek and set the part bed temperature and the feed bed temperatures, which would be in here, and then that's it. At the point that you've populated the virtual build space with your STL files or your step files or your IGES files, you've populated the virtual build space with the files. You've chosen your desired outcome. In this case, we wanted to go for speed. Speed typically happens when you minimize the number of layers. So we let the orient feature get us there, and all of those parts came in with their appropriate scale parameters, their appropriate part parameters, and then the build itself has all of the build stuff. At this point, if we were able to send it to a printer, that would be the next command. I'd click a button over here, and voila, the build would be available to you at the printer. That's pretty much it about building, starting a job in SLS with 3D Sprint as the software that you do your preparation with. 3D Sprint's got a lot of power to do other things. I'll touch on those briefly. Let's say your desire is to segregate some parts because in the post process, you want to have hands on them in a different way. Let's say you're making a medical device and you want to keep that medical device off by itself until you're further along in the post process. What we can do is we can cage parts. It's kind of cool. So let's just grab a part. I don't know, this one. We'll grab a part and we'll build a cage around it. And that way, when we're doing our breakout and we look to get the part in hand, we go grab the cage. We carry it around until we want to cut the part away from there. And yes, it sounds like a support structure, but it's not a support structure. It's more of a organizational technique. So if I had a collection of parts, I could cage them too. For this demonstration, we're going to do a freeform cage around a scale model of that University of North Carolina at Charlotte manifold for their Formula SAE car. Oh, so let's generate a cage around there. And when we do, it's going to create a group. And a group in SLS terminology is a collection of STL files that maintain their orientation to each other. They're still individuals. They are still unique, and they still can be treated individually with parameter settings, for instance. But the group has an orientation that is maintained throughout. So I see that we have this group now, and it is outside of the printing vault. So I'm going to go and just quickly auto place that. And I could have just grabbed it manually and moved it, but I wanted to demonstrate that the software will move it for you. So in this case, we see that it's not as efficient a build as it was initial. We'll go to a front view, and I can do, let me go to a left. I can do a couple of things, like I can grab this part and move it. And I can move it down to the least Z, and then I can move the parts that it might collide with a little bit, and then get to the point where I have a relatively short build, but now I'm accommodating this new thing that we've entered into the build, the cage about this part. And imagine, if you will, that it wasn't a cage around one part, it's a cage around a collection of parts. And I did that so that they were tied together until some point later in the post process. So one of the things that's different about moving parts in 3D Sprint versus the software it replaces is, if I grab this part and move it, it will not let me move it outside the bottom. So here doesn't matter how hard I hit, I can't get it to go outside in this case. And what I can do now is go back to top view, and I can select this part, and I can move that ever so slightly, and I can take this part again, and I can move it with a rotation, grab the handle, something like that, go back to a move. So I have all these options to get the parts into the virtual build space, where I want them. Right now, this would be out of bounds because it's going past that little dashed line. That dashed line represents an area that we would try not to use in the SLS space. But in any case, we can now, we've done this change. We can now go back to what we did initially, which is select everything and auto place everything for the least Z. Height as our priority. Okay, so we just learned another lesson. Well, okay, so first time we did it, we had a 125 millimeter build. Then we did the orient, where we said build in the least number of layers, and then we auto placed that, and it came in at 95 millimeters. And now we've caged a part, so that part is essentially taller than it was. We've gone back and we've done the auto place again with this now taller version of the caged intake manifold, and our software in an automated way is returning now a build that's 112 millimeters tall. So not quite as short as it was before we caged it, but still 13 millimeters, 130 layers shorter than the original orientation. Another thing I won't get into because I don't have a part up here to demonstrate well anyways, but another thing that the 3D Sprint software does very well compared to its predecessors is the hollow function. If you have a large blocky part in SLS, you may in fact not need all of the volume in it to be filled. So in an attempt to have something almost like a sparse mode, you can take that part and you can hollow it, and it asks you how thick you want the wall to be. In SLS, generally a couple of millimeters is just fine. I don't think this part has much in it that is that thick. So for demonstration purposes, I'm going to say, let's make it a 0.5 millimeter thick walls and hollow otherwise. And let's go to view and see if we can clip it. Aha. So we'll zoom in there, and you can see that it hollowed out the part, everywhere that we see here. I would argue that I'm doing this for demonstration purposes, not to claim best practices. But if I had a large blocky structure that experience told me the SLS process doesn't need to draw all of it. I can use the 3D Sprint hollow command and end up getting rid of a bunch of scanning that would take place on the interior of a part. And I'm here to attest that the function of hollowing in the 3D Sprint software is much more efficient and comprehensive than it was in older versions of our print preparation software. And with that, we'll send it back to Jason, and we'll talk soon.
Awesome. So I appreciate everyone that stuck around through all of this. I know we went a little bit longer than we had planned, but I hope you guys got some good information out of everything. So like I said, feel free to reach out to us with questions. You can reach us at info@nota3d.com or just our website, www.nota3d.com. Otherwise, I'm sure we'll also follow up with everyone that hung around this long, just to see if there was anything that we could do to help, or any questions we could answer, or if you had interest in diving into this more further. So again, thank you very much, and I think we will wrap it up with that. So hope everyone has a great rest of your day. Thank you.